So let me just remind you what we did last time. Today we have less time, but also the thing I want to say today is kind of just technical proof. So I will just give you a rough sketch of it because we want to move to basically discuss a little bit about basically correspondences between quantum cohomology and quantum groups as well. So just talk a little bit further about the proof, how it went, and then from next time we move to other topics. Okay, so let me give you a review of what we did last time, especially that one of you wasn't there. So this is what we did. So this is a review. So we discussed about this Nakajima basis for cohomology of an algebraically smooth surface, especially C2. So right now we are discussing quantum cohomology of Hilbert scheme of points with rational coefficients on C2. Okay, so then we defined some Fokker space over here, and we actually saw that we defined Clifford algebra, Heisenberg algebras, we defined a Fokker space, but we did everything for equivariant quantum cohomology, so equivariant cohomology theory of T-equivariant cohomology theory of the Hilbert scheme. And then on this space, we defined an operator. So this was our operator. We called it MD. This D is the tautological divisor in Hilbert scheme of points. It's exactly the locus where two points come together. You can see actually that defines the divisor. And this MD is an operator which is defined this way. T1 plus T2 divided by 2. These are the equivariant characters of the action of C star squared, that's our big T, C star squared, acting on C2. These are the equivariant characters, and so we define some operator like this. Something like this, times k bigger than 0. These were our Nakajima operators, P minus K, Pk. Creation and annihilators operators. And basically this thing is what we call it energy operator. In some sense, as you can see, it takes, roughly speaking, it dualizes an operator and look as a trace, the inner product. Energy operator. And then this M itself, this is M minus that, and this M itself was some function of this formal variable Q and these equivariant characters T1 and T2. And it was defined the following way. It was defined as T1 plus T2, K bigger than 0, minus K over 2, minus Q to the K plus 1, minus Q to the K minus 1. Again, P minus K Pk plus 1/2 the following sum. K and L bigger than zeros of T1 times T2, P K plus L, P minus K, P minus L minus P minus K minus L, Pk Pl. We call this thing a splitting operator. Okay, so on this quantum cohomology over here, so basically this thing, we define a notion of cohomology-weighted partitions of some integer n, and before defining the quantum cohomology, we looked at the T-equivariant cohomology theory of the Hilbert scheme, and we just realized that the Fokker space, basically the equivariant cohomology theory, is an extension of Fokker space by this polynomial ring in T1, T2, which is basically just the consequence of the fact that all cohomology classes on C2 are described equivariantly in these variables T1 and T2. So for instance, our example was the class of the origin, which is basically just T1, T2 times class of C2. Or we had the class of the x-axis equal to 0, which was T1 times class of C2. Class of the y-axis equal to 0, T2 times class of C2. So on and so forth. So any other class that I want to pick in here, I can expand with respect to these pointed divisor classes on C2. So everything will be in taking values in this polynomial ring in T1 and T2, and especially our operators. So then we had this theorem, which was which was basically by Akukov and Pandey, that so if you look at the videos, you can see that cohomology of quantum cohomology of Hilbert scheme of points on C2 gets related to Gromov-Witten invariance. And we drew even some pictures back in the past two sessions, how the threefold geometry relates to Hilbert scheme picture. So this is their theorem that MD is the operator of small quantum product, quantum multiplication, by the divisor T in T-equivariant cohomology of Hilbert scheme. And in fact, this immediately has a corollary, which is the following. These are, by the way, just review. These you can find in the previous video. Corollary is that the divisor class D, everything was defined as a vector. Divisor class D generates quantum cohomology ring of the Hilbert scheme of rational coefficients. Okay? All right. Okay. So what is the proof of this theorem? We wanna just roughly sketch the proof today. So first of all, before I go forward, do you have any questions? Anything so far that you would like to know about, especially if you missed the class? Yeah, let me just, yeah. Yes?
Can you say a little bit about the y subcoloring of the theorem?
Yeah, so that I will right now. So basically, proof proof of the theorem is the following. Okay. Proof. So the proof is that we must prove that the matrix elements of this matrix MD yield T equivariant 3-point functions of the Hilbert scheme. So in other words, we would like to prove the following, and I claim that as soon as you see this, you can see what it means. So we have two cohomology classes in the equivariant cohomology theory of Hilbert scheme, and we would like to look at this trace. We act by this thing. This was an operator. It acts on a state vector in the extended Fokker space, which we have extended to the polynomial ring in T1 plus T2. This thing is an operator that acts on this, gives you a state, and then I can talk about inner product between the states in that cohomology theory. So this, we would like to show this is equal to summing over all possible d's bigger than 0, q to the d, mu d mu. And this is the 3-point function defined by the 3-point Gromov-Witten invariant. So this is Gromov-Witten invariant of this thing is basically so this thing 0, 3 beta, if you remember, this was defined as integral of evaluation maps pulling back these cohomology classes to the moduli space of compactification of the moduli space of genus series stable maps with 3 marked points to your variety, which for us is going to be the Hilbert scheme, with given cohomology class beta, which for us is going to be d times class of P1. So that's what it means, degree d. So this is what it is. So on this side, you define an operator induced by the state vector associated to the divisor, tautological divisor of your variety, which for us is going to be the Hilbert small points. And you can generate all of the other states with respect to that. And this inner product, the structure is captured by small quantum product. Okay, that's what it is. Okay. So then we discussed about something in here which is actually looking at this particular moduli space, and we realized that because C2 has holomorphic symplectic form, honest holomorphic symplectic form given by that, and it has a, this is still, we are trying to do T equivariant. This has a T representation in here, which I can call something alpha. Alpha is the T representation of this form, and it has weight, some weight which is weight of this plus weight of that. So in particular, actually, we realized that this holomorphic symplectic form on C2 naturally induces 1 on the moduli space of points on C2, on the Hilbert scheme itself. So Hilbert scheme itself is equated with the holomorphic symplectic form. And that thing also equivariantly has weight T1 plus T2. But in particular, it's a known fact, and I discussed it last time, we showed it. It's a known fact that On varieties which are equipped with holomorphic symplectic form, your virtual cycle might vanish. So for instance, K3 surfaces is one of those things. So the isomorphism that holomorphic symplectic form induces between tangent and cotangent bundle of your variety actually ensures that the obstruction bundle of your moduli of stable maps, the obstruction bundle is the one whose integrate we are taking. We are taking some top Chern class of the obstruction bundle, and we are collapsing it against the virtual cycle. On a variety which has holomorphic symplectic form like this one has a trivial factor in it. There's some trivial bundle in it. And the top Chern class of this will vanish. So you will naturally get zero invariance unless you take that trivial factor out. And you do this derived categorically. The obstruction bundle is given by cohomology of the obstruction theory, certain cohomology of the obstruction. If you have a perfect obstruction theory like E dot, which is a map in the derived category to the cotangent bundle, cotangent complex of your moduli space, with certain nice cohomology vanishing conditions, then your obstruction bundle literally is given by H1 of E dot dual. That's your obstruction bundle, which in this case, we discussed last time, it has a trivial bundle inside. It has, in fact, a trivial piece inside. And that trivial piece precisely corresponds to this holomorphic symplectic form on your variety, which as a T representation, it carries weight T1 plus T2 again. Okay? So what you can do is you can apply certain truncation operation to this thing. So for instance, you can maybe dualize this, and then there is a map from here to its H1. And as an object in derived category, this sits in degree 1, so I can shift it by -1. And then I can take the cone of this thing, cone of this map, and then I can, okay, it's not like this exactly, because this literally is the obstruction bundle. So I can then apply certain trace, and I will get this, eventually I can spit out this trivial bundle. Then I can look at basically the whole composite map, and then I take the cone. And take the cone of the composite map from here to here. And I shift it by -1, and that guarantees that the cone shifted by -1 gets mapped to the potential complex. Whatever that theory is, if I can show that it satisfies the properties of deformation obstruction theory, that theory has an obstruction bundle which eventually doesn't have this trivial piece in it. And that can reduce the non-vanishing invariant for us. Okay, so that's the thing that we did last time. It's not as sloppy as what I said now, but I'm just reminding you of the analogs of this thing that we did in the past time we discussed it. Okay, so we did this last time. So we reduced our obstruction theory, and that induces a reduced virtual cycle. The main feature of the reduced virtual cycle is that it doesn't have this trivial piece with this T weight in it. Okay? So in fact, we showed that, how did we do it? Yes, we showed that there exists a reduced virtual fundamental cycle for M bar 03 C2 and D such that its relation to the honest virtual cycle is the following way. So M bar for all genus actually satisfies this thing is C1 of some C representation, some T representation of the holomorphic symplectic form in here, coupled with M bar Gn C2n Q virtual reduced. And this thing is just the T weight of the holomorphic symplectic form, which is equal to T1 plus T2. right? So these are just cohomology or homology. These are Chow homology classes in the T-equivariant cohomology theory of the moduli space. Of course, it makes sense the presence of variables T1 and T2. This is equivariant cohomology. And I'm just saying that after reducing and taking out this homomorphic symplectic piece, or the bundle, trivial bundle, you will see this relation between the virtual classes. Okay. Again, this we discussed. So this actually suggests, and it is the case, that in the honest calculations, when you want to match on one side the 3-point functions on the Gromov-Witten side with the trace of this matrix MD on the quantum cohomology side, we need to match things modulo this factor of T1 plus T2. Your invariants all see a factor of T1 plus T2 because you will calculate some number in here and you will, it is coupled with this factor of T1 plus T2. So your invariants all have positive valuation with respect to this term T1 plus T2. All right, so yes, so how did we do it? So yes, here, note that when you remark, note that with respect to equivariant, with respect to T-equivariant identity class in the equivariant homology of C2, which is the point class, our vectors can have the following description. We can have basis elements mu and mu in the equivariant homology of the Hilbert scheme given by, so this basis element can be spanned in terms of the identity, the point class in the equivariant homology. So this actually can be written as this, and it will be something like T1, T2 to the length of this partition mu. This is a partitioning of the endpoints weighed by cohomology classes inside, which are the three classes. Times mu. This is what it means. If you take this into account, then I can rewrite what this is. D. I can span one of these things, and I can write it as, well, you know, you really are caring about product in here, but we can write things with respect to here, so that means divide this by this term. So this is basically 1 over T1, T2, length of the partition, and then you can write this as homology class, spanned by the point class of the origin in equivariant homology, D. Or you can use the other one, actually. It's also the same thing. So this is 1 over T1, T2, length of the partition mu D. That's what we are going to use, actually. Remember that this is it's not something very complicated. When we were defining the Fokker space formalism for equivariant cohomology, every state vector in the Fokker space is defined by action by these annihilation and creation operators actions on this identity vector, which was the vacuum vector in our Fokker space. Now we have constructed this Fokker space analog of equivariant cohomology, and every class can be described by the action of the operators, Nakajima operators, on the point class, which is the identity of the equivariant cohomology class. So that's why we are doing this. Okay, so it rotates the vectors in the vector space. Every state is a rotation of the vacuum vector somehow. If I can call it a rotation. Okay, and this thing is just, so now we can have a lemma, which is the equivariant Gromov-Witten invariance of C2, the Hilbert sum of endpoints on C2 of positive degree with insertions on in equivariant cohomology theory of the Hilbert scheme are divisible by T1 plus T2. Well, this right now is not so hard to see actually, right? Really, it's because some number like this guy is described by basically the pullback of the corresponding classes. So therefore, let's say I have expanded by mu0. This kind of thing is topped with pullback of the third cohomology class, capped with T1 plus T2 times M bar 03 C2 and Q virtual reduced. That's why. So this thing gives you the reduced invariant, and you can actually see that you have divisibility by this T1 plus T2. And for this guy, let's give it a name. So I can give this a name. So this, I call it broken bracket means honest integration, and the curly bracket means the reduced integral. Against, basically collapsing against the reduced virtual side. So I call this mu0 d nu degree d. That means reduced, the reduced invariant. Okay. Now, what is the procedure that they actually use to check this? What can I say? So some sort of sketch of the proof. They use induction. So let's see. Should I mention this or not? So. The proof is given by induction on n and d, on the number of points and the degree of the curve. So if n is equal to 0 or 1, then that implies that NB vanishes. At the same time, it also implies that B will become equal to 0. So the statement of the theorem is true. So the theorem can be done for n bigger than. Okay? So let n be bigger than 1 be proved by induction on b bigger than 1. That's how the proof goes. Now, what I'm going to do, I'm going to basically tell you the following. The strategy is as follows. So we are going to use induction on D, and then it turns out that this kind of Gromov-Witten invariant can be captured for all possible cohomology classes mu and nu from certain building blocks. So we would like to look at certain class of basically configurations of points on the C2, that these two will be mu and nu, and prove the statement for those things. Those are the building blocks. And then you have this additivity statement that you can increase the classes, and you will have control over what happens when you increase the classes in a particular form, and your integrals would obey the same behavior, basically. That's what we are going to do. Okay? So let me just basically mention some facts which are important in this calculation. So some remark. Consider mu0 b and nu, the reduced invariant. Let C be sum of mu I class of pi, I from 1 to length of the partition mu, be an element in the symmetric nth product of C2. We have discussed that there is a map from Hilbert's scheme of n points to symmetric nth product of C2. And we call this map Hilbert-Chow map. So, in fact, we know that these classes, mu and nu, these are certain partitioning of the length n subscheme of C2. So in particular, I can take an element in here, a point in here, given by this point, right? So a point in here is a subscheme of length n on C2, and a point in here is a subscheme of length n, which is clustered on n distinct points of C2 by these mu I, and the sum of the length of mu I is going to be n. All right? So there are n many partitions. So I can pull back a point in here, and that defines for me one of those mu's. So by definition of Nakajima basis, we can replace the covariant class with 0 by the class mu of C. C in particular gives us a partition of an n, partition of n. And we know that the elements of the Nakajima basis are elements we obtain, are state vectors we obtain by looking at cohomology weighted partitioning of n. This is exactly cohomology weighted partitioning of n, where the cohomology classes are the point classes. And so we can define mu C, and we defined this last time. This is something that keeps track of the automorphisms of the partition. can look at the preimage of this point in G. That gives us a cohomology. And then, what does this imply? I can investigate what happens for this in my invariant. If I replace mu with this particular class, what happens? Okay. So note that every rational curve to C to N contracts to a point. Under the Hilbert-Chow morphism. Okay. This implies that the moduli space of the stable maps of maps connecting mu C and nu is isomorphic to moduli space maps to I from 1 to n length of mu of Hilbert scheme of these many points concentrated at the point pi on C2. Right? Because now our cohomology class has this particular form. These are n distinct points which do not move. And our stable maps basically contract via the Hilbert-Chow morphism. So the moduli space that connects these two guys will become isomorphic to moduli space of these guys if length of mu the same as length of mu and empty otherwise. And okay, so these are the punctual difference schemes. So then you can ask yourself, what's the moduli space of degree D maps to this thing? When you send a degree D map, let's say you're looking at the non-empty component. Send a degree D map to here. Then that basically tells you that you need to distribute D, how much of the degree D map will be distributed to each factor. Right? So how should I say it? This shows that our moduli space symbol 03 build mu I di of C2 D decomposes into a union of connected components depending on distribution of D to each factor of the product. you haven't seen this notation, this is our homology weighted partition. It's a vector of tuples, mu1, gamma 1, all the way to mu length of the partition, gamma length of the partition. Meaning, length of the partition means how many of these parentheses. So, these are partitioning of the n. And instead of calling them n1, n2, all the way to n of length of the partition, instead of indexing them by 1, 2, 3, I index them by cohomology classes. So it corresponds to basically loci in my original C2, where the points lie in cycle given by the Poincare dual of gamma 1, or all the way to gamma last gamma. Okay, so that's okay. So we discussed about these things. If you look at 2 sessions before, you can follow this completely. Of course, this, when I put it in here, in my product, which I erased, this has a separate meaning. So when you put this into Nakajima formalism, you're defining these corresponding operators as correspondences between Hilbertissimo of different number of points. The creation and elimination operator. This is an operator from, let's say for creation operator, it takes it from cohomology of n points to n plus k points. And the elimination operator as well. Okay? And for those things, you need to look at how we defined it last time. So you're looking at tuples of I1, I2, where I1 is a subsheaf of I2. Both of them are ideal sheaf of points on C2. And the co-support is a skyscraper sheaf. It's a sheaf supported on some length n zero-dimensional subscheme, which is supported at a point which lies on dual of gamma 1. It's involved. We did all of it last time. So. Okay, if you didn't come to the last session, it will be very vague what I'm saying now, but we did it very rigorously in the last 2 sessions. Okay, so to the product. So on Okunkov and Panterban, they show that the only components of M bar 03 are the ones where D is distributed entirely to a single factor. So for instance, something like of C2 mu IPI for some I. Okay? And then, after somehow unraveling the definitions, this tells them certain properties of quantum product on this Fokker space. So let's put it this way. After unraveling definitions, we show that. So firstly, they show that mu for D bigger than 0 is equal to 0 for mu not equal to mu. This was because of the Hilbert-Chow morphism. And then they show what happens if I take a class and I quantum multiplied by itself. This becomes some gamma nd times t1, t2 to the minus length of mu times t1 plus t2, where gamma nd is some rational constant number. And we also show that this is something called addition formula. So this is addition formula. They show that basically mu d mu for d bigger than 0 divided by intersection pairing of mu with itself in the focus space, this one, is equal to summing over all I mu I d mu I. Mu I mu I. This is also what they show with respect to that decomposition. So they show the same statement also for MD. They show something similar. So mu and d mu is given by mu I and d mu I divided by mu I mu I. But these they verify these properties. They have the moduli space. They use the Hilbert-Chow morphism to see how the moduli space decomposes into n products. Then they argue that, can I really distribute? I'm sending some curve into this multifold factor of the Hilbert scheme of punctual Hilbert schemes of points concentrated at points pi. How can I send my curve over there? It's a curve of degree d. I need to distribute the degree of the curve into that multiple component. Then they realize that, in fact, if you distribute the degree into di and dj, even, for I and j not equal to each other, your invariant vanishes. So the only non-trivial components are the one where you send this to one of those guys. You distribute d to one of those guys. And then they argue on that particular component, basically what's the invariant? What are the properties of the invariance? So these two they hold true for every component, and then the total sum, this is the additivity. The invariant is the total sum. So where for each one, you're just looking at degree d maps to one of the components I, and you're adding them all. That's additivity. Okay, so now let's do one example. So I told you that this calculation eventually reduces to calculating certain building blocks. Let me just talk about a little bit of those. So what are these building blocks? Essentially, the key ingredient of this calculation, and the paper is really involved. So the key ingredient is basically this one. So they would like to argue by calculating this thing, in minus 1 and 1. This is the building block. What it means, where I of lambda denotes the T fixed monomial ideal corresponding to a partition lambda given lambda is equal to the monomial xj minus 1, yi minus 1, box equal to ij's, not equal to lambda, which is a submodule of the ring of polynomials in x and y. So what is going on here? You have these, and you have the additivity. So on each one of these components, you know these properties. You know that this will vanish for mu not equal to nu. Then you know what's the self product, and you know that by additivity, what you want to calculate is becoming sum of these invariants on each one of those derivatives. Okay, so let's look at one of those guys, and over here we want to calculate these. Okay, so you're doing T equivariant integration, so that means that you're localizing your integrals. So if you have sheaves, ideal sheaves of points, the T fixed ones are the ones whose co-support is fixed by the point, by the torus. That is just the center of the C2, origin of the C2. And if you have ideal sheaves like that, then they must be given by monomials, otherwise they move around by the action of C2. So this being monomial is obvious. Now what does this notation mean? Well, you know, if I give you some Young tableau type diagram in here, if this is the x-axis and this is the y-axis, then I would like to construct these Young tableau diagrams and obtain a one-to-one correspondence between the diagrams and the t-fixed points of my Hilbert scheme. So for instance, if I have some box in here, so this I would like this coordinate of the box, let's say, or you can choose whatever you want. Let's say this coordinate of the box, I would like to represent for me x. Okay, x to the 1. And I can also have y squared, and so on and so forth. Okay. So let's say I have some box in here, okay, which is x, for instance. Then let's look at this. You agree that if I have some monomial x given by the ideal, if I have this partition x, that means that all powers of x and all multiples of x by all powers of y will be inside this ideal. So as a representation in here, basically you can see that all of this space is going to be my ideal. As a Young tableau diagram, I'm just seeing the box. So those are the ones which are not inside my partition. So let's say I have some configuration like this. Then I can actually, from here, from this finite configuration of boxes, I can read off what are the generators of my monomial ID. Right? So this, yeah, so basically everything, but this is my ideal. All of these boxes will be functions which are covered by my ideal, and this represents basically the equivariantly, or the module basically, given by Cxy mod I of lambda. And lambda is the partitioning of, let's say my subscheme is length n. I need to basically tell you how my monomial configurations partition this n. So basically I would have n boxes in here. Let's say now like this. This is a particular partitioning of n. Right. So this represents the skyscraper sheaf of the zero-dimensional subscheme of length n with this given partition. Right. it is like this, then I don't know. So you need to give me some good models of that thing. So let's say it's like this. Something like this. So what are the generators? So x cubed, for instance. Then maybe everything beyond x squared and y is there. Everything beyond x and y squared is there in my picture. This is this corner, and then this corner, right? Everything beyond y cubed is there too. So you just read off the coordinates of the corners, left corners of these boxes. That gives you your ideal. And then this gives you, on the complement of the ideal, gives you the skyscraper shape. So this gives you a one-to-one correspondence between this dark picture, between this combinatorial picture, and the t-fixed points of the Hilbert-Small points on C2, generated by these monomial ideals. Okay, so this is what we are doing. So yeah, they would like to calculate this kind of product. The map lambda to I of lambda is a bijection between a set of partitions given. So yeah, so by this we mean these boxes which are not inside the partition. Partitions of n, I call it Dln, and the set of t-fixed points of C2 and T inside. Just the picture, just putting things in words. This gives a bijective correspondence between partitions of n and the t-fixed points, which are actually these guys. These are the t-fixed points. Those are as combinatorially are given by boxes whose ij coordinate, a box in here with an ij coordinate, does not belong to my partition. So that's what it is. And the eigen vectors of MD0 are determined by, this is an operator and it has eigenvectors. The eigenvectors are determined by, I call them minus C lambda T1 T2, which is given as follows. I and j's in lambda j minus 1 T1 plus I minus 1 T2. For a given particular partition. The eigen values. Okay, eigen values. For lambda, a partition of n. This sum is the same as the trace of T action on CXY y island. If you actually read off the coordinates of your partition, they are given by monomials, x and y's, and the torus is acting on C2 with equivariant characters T1 and T2. So x to the I has weight I times T1. Y to the j has weight j times T2. So the trace of this action on the skyscraper sheaf given by this monomial is a polynomial in variables T1 and T2. Finally. It happens to be the eigenvalue of the operator that we define when it acts on C. Okay, so, and how do they do it? Now the T fixed point is given by a certain ideal sheaf, right? It has some class. But when we lift everything into the focus space, it has some image. So the T fixed point I of lambda has an image in the focus space given by, notationally, we call it J of lambda, and this is an equivariant cohomology of our Hilbert's scheme. This is the focus space extended over Q with this polynomial ring and equivariant parameters T1 and T2. Give me a second. Something I wanted to. Yeah, that's fine. Okay. And this is this thing is called the Jack polynomial, which has a specialization to Shor functions, and you can see this in the McDonald's book as a book on these things. So these are Jack polynomials which specialize to Shor functions. And this is, by the way, this is summing over all n, the equivariant. This is what we are here doing. Okay, these are the Jack polynomials, and these guys actually, Kunkov and Panderbande, they find a specific description of these things. So every time you give me an ideal of certain length n subscheme of C2 with a certain partition, they tell you what is the Jack polynomial associated to that, which is an element in here. And so now intersection of I mu is going to be the intersection of the Jack polynomials. Associated Jack polynomials. So they show that, this is by Rufo, Akunkov and Panderbande, they show that these are equivalent to minus 1 to length of lambda times length of lambda factorial divided by dimension of lambda sum over mu T1 to the power length of mu plus lambda modulo T1 plus T2. This is what they show. This is the dimension of representation lambda of symmetric n group, Sn. And this is certain character of evaluated certain character of lambda representation. Lambda evaluated as conjugacy class mu. Anyway, all of this is in the paper and also in Mathieu Macron. What matters right now is Jack polynomials. So as soon as this is very computational now. If you believe in these things, you give me a certain configuration concentrated around the origin, certain ideal sheaf of length and subscheme, certain configuration in the Fokker space, in the equivariant cohomology theory of the Hilbert scheme, it's associated with the Jack polynomial. An intersection is given by J lambda J mu. After this, everything just becomes computational. We're not supposed to go to gory detail, but just reviewing what are the ingredients and so on. But this is this kind of like sketching of what others did. So. And it's pretty technical. So this is what now they can calculate. So they calculate the following. Remember that we were trying to compute I n d I n minus 1 and n and 1. And they show that this guy becomes equal to eventually something like this. Minus 1 to the n, e1 to the 2n, n minus 1, n factorial squared, modulo t1 plus t2 squared. This is their final calculation. So they realize in particular that they need to check the statement. Now this is all in the Fokker space, and the equivariant cohomology, and in terms of acting by this operator on this guy, and the Jack polynomial induced by this monomial ideal. And they calculate this. So now when they want to match, they realize that they need to match things modulo t1 plus t2 squared. So on the Gromov-Witten side, on the quantum cohomology side, the 3-point functions, they need to match with this thing modulo t1 plus t2 squared. That's what they want. This is just honest result of calculation. Okay, and it's really detailed. I'm just putting for you the answers. Okay, so what happens on the other side? So calculating the 3-point invariant. again, our building block is still this thing. This is what we would like to calculate. And we are expecting that this should be something that modulo T1 plus T2 square matches with this. And again, this thing is, as we saw, this is already itself T1 plus T2 times IN11. This is the reduced invariant because of the reduction procedure that we applied. Now remark, since we need to match the two sides, modulo T1 plus T2 squared, we realize that we can do localization with respect to subtorus T prime subtorus of T, where T prime is defined by T equal to one factor T, which is equal to either T1, instead of T prime, maybe I call it T plus or minus. The subtorus in here, which is defined by minus T plus or minus. So we are looking at the subtorus where T1 plus T2 is equal to 0. Right? That gives us the extra factor of T1 plus T2. That we want. Okay. So, key observation, the T plus or minus fixed points of C to N are the same as T fixed points of C to N. However, M bar 0, 3 C2 and D, T plus or minus, is a much larger set. Than M bar 0, 3 C2 and D, T. So there, the analysis was somewhat delicate, and it had to do with keeping track of what exactly the Jack polynomials are and how is the intersection there. Here, the analysis boils down to understanding precisely what are the T plus or minus fixed loci of the moduli space of 3-pointed rational curves inside. And again, I just summarize it. So this has to do with these loci of broken or unbroken curves. So what are or maps? what are the broken maps? Consider m bar 0k c to n d for d bigger than 0. Let f from c to of n be a t plus or minus fixed map. Okay. Now, if P is a marking of this curve C, a fractional T plus or minus weight WP is defined by T plus or minus representation of the tangent space at that point, tangent space to the curve at that point, of tangent of the curve at that point. This is obvious. Now let P in CR, and obvious in the sense that we have done it many times in this class. It's a definition. Let P in C be a component incident to a node S in C, then the P plus or minus weight W big P C or S is defined by tangent of P at S. What are we doing? You look at the T plus or minus fixed loci of the moduli space of the stable maps. You eventually see that the T fixed maps are realized by certain graph theoretic data. And the graphs are all decorated with these weights. So then you need to divide by whether or not you have connected components of your curve adjacent to a node or not. And all of it is given by T plus or minus representations, basically, which are given by these weights. So for the node, for the components where connected components P, which are incident to a node, you just take a tangent space to that component, add that node, and calculate the T representation, and that's your weight. And otherwise, this is your weight W. This gives you the graph theoretic data associated to this T fixed map, the stable map. And okay, so what does the broken and unbroken mean? Definition: a T plus or minus fixed map F is called broken if one is source curve C contains a connected F contracted component C tilde such that the disconnected curve C minus C tilde has at least two components, connected components, which have positive degree under F. Or part 2, the two non-F contracted components P1 and P2 in C meet at a node S.
In this definition, C tells the amount of the empty F contracted component.
No, I mean, because then we would like C minus C tilde to be disconnected.
So the answer is yes or
No.
There must be some.
Yeah. Or otherwise, it's just. Yeah, it should be a subcurve. And two non-F contracted components P1, P2 meet at the node S of C, and have tangent weights. Now we know if they are a component incident to a node, we can calculate the tangent weight by looking at the C representation over there. Now tangent weights WP1 at S and WP2 at S such that WP1S plus WP2S is not equal to 0. Okay. So in this case, this is called, this C tilde, this is called the breaking subcurve. This is the breaking subcurve. They call it breaking subcurve. And this node S, this is called the breaking node. Okay, but what is the point? You look at your curves like this, you have breaking subcurves and breaking nodes, and you realize that your moduli space, this guy, the T fixed loci of your moduli space, this becomes union of two connected components. The components of T fixed broken maps and the unbroken maps. This you need to investigate. So this, if I call this M, they realize that this becomes M broken, M unbroken. This is the first step of their proof. Okay? Then, actually, this suggests that their product becomes product over the broken loci plus the product over the unbroken loci. Okay?
In this denotation, is n broken. I guess n broken is compact. How about n unbroken is vice versa?
Yes, yes. Yeah. Yes. I mean, remember that we are doing, everything will be compact anyway because we are looking at T fixed loci. And Then the next part of the proof is that to show that these guys do not contribute. So the contribution only boils down to these guys. And eventually they calculate this guy. So I just put for you final contribution and basically finish it because I'm just reviewing and there's no point of going to glory detail. Basically this is the final answer. So they show that mu, I mu, I should have called these things, it doesn't matter. So I mu I n d I n minus 1 1 d plus or minus a unbroken becomes equal to minus 1 to the n plus t minus 1 t1 plus t2 t1 to 2n and factorial n minus 1 if n doesn't divide t and this term n factorial squared if n divides. And in fact, because I don't have time, they realized that the unbroken maps to the Hilbert scheme of points on C2 are given by a certain line in the Hilbert scheme. Only a line in the Hilbert scheme that connects in to in minus 1, comma 1. That's the only one. And they calculate particular the contribution for that particular component. All right, so this actually confirms that the final result that we want. So this calculation and the one that you have by basically acting on these cohomology classes by this MD operator on the Fokker space, these two things match eventually modulo T1 plus T2 squared. This is the final problem. So this proves the correspondence. So eventually, and these are the building blocks, remember that. You have pulled down everything to the building blocks. So this eventually shows that some quantum operator MD acting on nu on the Fokker space of the equivariant cohomology theory of Hilbert's scheme of endpoints on C2 matches with summing over all degrees mu d nu d, where this is the tautological divisor of the Hilbert scheme of endpoints, and these are cohomology classes. So yeah, this is very, very rough, but I was trying to review for you to know kind of what are the ingredients that they use and so on. If you actually want to do some example, you literally need to do step by step reproducing all of their ingredients and see what you can get. Yeah, okay. That's it. Any questions? Okay. Cheers.
We still have 3.